So today we will spend about half the time discussing midterms and what happened in January, and then we will go on to the future part of the course. So we were discussing the course review last time, and I went and listened to some of my lectures on the video, and definitely my voice sounds quite bad when recorded or on the microphone. The only local fix I can think about is that I will really slow down, and the second is, if you help maintain more quietness in the room, then even my bad voice will hopefully get across a little better. Okay. And I will monitor this for the next month. We'll have another survey, especially on acoustics and speaking. At the end of February, if there's still some trouble, I'll probably go and see a speech therapist. Okay, so quiz questions. There were 3 questions in the quiz. If you don't get the first one at all, that's my fault. If you don't get the second one, that's your fault. And if you don't get the third one, it's undecided. We don't know whose fault it is. If you get at least half the paper right, you're doing okay. It's in the sense that don't worry about grades if you solved at least 1.5 questions reasonably well. If you solved all 3, then you're sort of done. If you decide to not come to class, well, not that extreme, but well, there's still a lot of fun stuff to learn. So the first question tested a whole bunch of different things. The first issue was, how are these characters and integers and long ints interacting together? So what we read from role of position is a character. Okay. These characters like quote 0 through quote 9, they don't represent the integers 0 through 9. They actually represent some ASCII code, which is an integer between 0 and 255 inclusive. When you do operations on them which look like arithmetic, and that includes relational comparisons, like if quote 0 is less than equal to roll pause, that is an arithmetic comparison. Implicitly, the system will think about both sides of the comparison as integers. And therefore, quote 0 will be transformed to the ASCII code for the character 0, and roll pause similarly will be transformed from a character inside the string roll to another integer value, and then those 2 integers will be compared. Fine. After that, the main operation done inside the body of the loop is ch, which is a long int, 64 bits, equal to roll pause minus 0. Okay. So in case the character at position pause was quote 0, this will result in the integer 0 going to character. If the character was the quote 5, then this quantity will be quote 5 minus quote 0, which is the integer 5. Okay. So in all cases, if the input character is a digit between 0 and 9 inclusive, that will be transformed to the corresponding integer between 0 and 9 inclusive, and that will be stored in ch. Okay. Similarly, in the second if clause, we will be testing whether roll pause is between a and z, and then we will subtract a from it, which means that the resulting raw value will be between 0 and 25. After taking this value between 0 and 25, we will divide by 16 and take the remainder, which means that the resulting value will be between 0 and 15, okay, which is 1 hex digit. In both cases, ch gets a value between 0 and 15 inclusive, which is worth 1 hex digit. Okay. Now, I don't know how many people have roll numbers with characters in them. Anyone with roll numbers with characters in them? So you have a D if you are a dual degree student, and there are some other cases. Okay. So D will result in 3. Okay. A is 0, B is 1, C is 2, D is 3. Now, the second issue we are testing is, how is pause behaving? We are not picking characters from the roll string one by one left to right. Okay. Somewhat reminiscent of the Josephus problem, we are running over the roll buffer using a pause which is stepped differently from Rx itself. Rx clocks from 0 to roll.size. Rx's only job is to count that it has taken all characters once. In fact, that is itself not entirely trivial. I took the stepper of 13 because for everyone's roll number, whether it has 10 digits or 11 digits, 13 is co-prime to that length. And therefore, as you step through with a step size of 13 and you take modulus, mod of roll dot size, you will actually exhaust each character exactly once, but in some arbitrary order. Okay. So if your roll number is 11 characters long, then although Rx steps from 0 to 10 inclusive, pause steps through 0, 2, 4, 6, 8, 10 followed by 1, 3, 5, 7, 9. You can easily verify that. Okay. So the second issue being tested in the question is, do you understand how pause is visiting elements of the roll array in some arbitrary order? Now the third issue is, how was num being updated in every iteration? It was initialized to 0, and then as you read roll pause step by step, num was shifted left by 4 bits, thus making space for 1 hex digit. And because of the shift left, those 4 positions were filled with 0 bits. Okay. And then this num was XORed with CH. Now CH, as we have already seen, is a small number between 0 and 15. So its higher order bits, apart from the low 4 bits, everything was 0 to start with. Okay. And this was XORed with the other element. So XORing with 0 gives you the original value back. Right. So in either way, this is equivalent to replacing the 4 least significant 0 bits with the 4 bits of CH. Okay. So if the current roll pause is D, then CH becomes 3. So the bits 0011 will be shifted into the rightmost position. So if your picture helps, this is my big 64-bit number, okay, and this is a hex digit. That's a hex. That's 1 byte, okay. And remember, I have 8 bytes in a 64-bit number. So here is the first byte. Here is the second byte. Here is the third byte. 4, 5, 6, 7, 8. Okay. So that's the num. Okay. So in case you have 4, then this is just 4, and then those are all zeros. So this 4 means 0, 1, 0, 0. And if that is 0, then this is all zeros, 4 zeros. So what happens is, when you supply the new, so this is num, and here is CH. CH is also a long integer, but its worthwhile content is only in the last hex digit, and everything else is zeros. This is all zeros. You read one character, you transform it to an integer, and you take modulus of 16. So the last hex digit is between 0 and 15, and that's the only content. Everything else will be zeros. So I mentioned that in a class, and it was also in the slide. In C++, if you say int or long, that is 32 bits. If you say long int, speak of unimaginative names, that is 64 bits. Now, I realized that I did not emphasize this very carefully in class. There is a discrepancy with Java. In Java, when you say int, that means 32. You say long, that means 64. Okay, it's possible that some people got confused because of that, and even I was confused initially. So if we see a systematic problem because you misinterpreted it to be 32 bits instead of 64 bits, we will take that into account. Okay. But in C++, you have to say this long declaration, a long declaration to make it long. So when you get this last digits, what the program says is that you shift by 4 position, which means this hex digit comes here and this hex digit is moved out, and then that input hex digit enters the least significant position. That's what the XOR does, really. Shift and XOR, that's what it amounts to. So in fact, the question was designed that you don't have to do too much bit arithmetic in your head or on paper. You see a number between 0 and 15, that same number goes into the last hex position, everything else gets shifted left. So printing it out in hex should in fact be quite simple if you understood what the code was doing. Okay. Yes? In C also int and long are supposed to be the same, but there are differences in compilers. Historically, C and C++ became a mess around the middle of the 90s. Different companies are building different compilers with different standards and conventions. And that's really why Java took off, because Java promised you exact same semantics on a particular virtual machine, Java virtual machine, on all architectures. This is why it came about. Okay. And that's why I was also confused, because I have coded on machines where long int is 64. You don't have to say long int. Any questions so far? So the summary is that there are 3 parts we are testing in this question, roughly corresponding to the 3 columns in the table, and accordingly, we'll look at grading. So here's the table, and in the solution key that we are going to publish soon, I've explained what we are doing and along with a sample. But of course, the exact answer depends on your specific roll number. Okay, and you will be graded accordingly. The code I will also post. To give you an example of the code running, so this is the same exact code as specified. So I'm printing in decimal RX and pause and CH, and then in hex the number. Okay, that's how you change the radix while you're printing using cout. Right? So I'll give an example of this. So I'll not give a standard roll number, we'll just play with different things to see what happens. So suppose I entered the roll number, which is just say A, B, C, D, E, F, G, H, I, J. So J is 10. Okay. So I enter just J. Okay. J is the 10th letter, so it's 9. So you just get a 9. Okay. So the 0th position is red. So Rx is 0, pause is also 0, it's 0% third, whatever length is. And then I get a J from there, which turns into 9, and then num is also 9 after the shift. Okay. Now suppose I entered J. So the nice part about this problem is every character you enter becomes 1 hex digit in the output. So you can just think of it character by character. You'll just get 99 because it just shifted and then another 9 goes in there. If I enter JK, that will be, any guesses? 9A, right? The next one, 10. It's just the next hex thing. Okay. So similarly, if I say JL, it will be 9B. Okay, if I keep repeating, and otherwise if I say, for example, say J2L, what will happen? It will just be 9-2B. Okay, depends on the order though. The length is increasing now, and at some point this stepping by 13 might kick in, but so far not. So J2, 9-2B. Now, of course, if you enter something long, then the stepping by 13 and division will kick in. So if I say 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, what do I get? I get it in some strange order, depending on how 13 modulo is stepping through the roll number. Okay, that's the actual position being accessed. That's the character being accessed turned into a hex digit. You don't see that here because everything was entered between 0 and 9. Okay. If I enter instead A, B, C, D, E, F, G, H, I, J, K, I'll get this complicated thing. Okay. You're still accessing all the even places first and then all the odd places. And if you work through it, you'll see that this is what you get. 2, 4, 6, 8, 10, 1, 3, 5, 7, 9. Okay. So 3 things to understand in the code: stepping through the array, converting characters to integers, and masking and shifting and XORing. So the next question was probably simpler than the first one, at least less tedious. So maintain a decimal number as you see more and more digits, starting from the most significant digit. So you first see 3, so you think the number is 3. How do you do that? We already saw from question 1, the input digit is a character, it's not an integer. Therefore, the integer you want is digit minus code 0. Okay, so that's one element we will test. Then suppose you see a 1, then the number changes to 31. And that's easy to do. We just take the old number, multiply it by 10, and then add digit minus 0 to it. Okay. So it's easier to read a number most significant digit onward. If I presented to you the number from the unit place onward, it will be a little messier. This is much cleaner. One line code maintaining the number as we see digit after digit. Now for printing a number, however, it's the opposite. It's easier to print the units digit first because it's simply num%10. Okay? And you can directly see out num%10 because that integer will be converted into a character inside the IOStream library as 0 plus whatever you gave it. That's how you turn things into characters. Okay? Now, to discard the units digit and brings the tens digit into the unit place, we all know how to do that. We simply divide by 10. So an integer division by 10 will discard the unit digit and bring the tens digit in. Okay. So that's how you print a number from the rightmost digit to the leftmost digit. Okay. Now given these two parts, one of the things we'll of course test for is that you put them together for the third part. That was the sole point of the exercise. So if we have to reverse a number in digits, part C just puts together parts A and B, we extract A, least significant digit first, and pack into B as most significant digit first. Okay. So the code is really simple. While the number A is greater than 0, I keep shifting B left by one digit and then put in the current least significant digit of A in that least significant position, and then I divide A by 10. So question 3, you need a little bit of geometry knowledge, but I assume that all of you have it. So to find a point internal to a convex polygon that is not empty, that is it has 0 area. If it has 0 area, there is no interior point. Otherwise, you can just take the centroid of all the vertices, and that's very simple code to write. Okay. What you do is you add up the x's, you add up the y's, maintain a count of what you have to divide it through. That's already given to you as n. Then you divide it. Okay, that's the centroid of the polygon. Other solutions are possible. You can find some non-empty triangle or other subset of the polygon and take the centroid of that. Okay, many other solutions are possible. Now the question as to is 0, 0 inside or outside, for each edge, okay, you have to test whether 0, 0 and x in y in are on the same side or different sides of the edge. Okay. And we know how to do that, which is you express the equation of a line as ax plus by plus c equal to 0. Now you can find a sign distance to the line from any point, and then you check if the signs are same or opposite. So that's requires a little thinking. Now we could have given away the exact solution about how to do that and tested you only on writing the code, but it seems like in real life you have to model such things starting from the physical description and then map it to the numbers. So this was a small test of that. And the area problem is probably even slightly easier because everyone understands that the area of a polygon can be decomposed. You can either decompose it based on x in, y in and have like pieces of a pie, star-like, or you can use any corner vertex like that and then you can triangulate it by connecting it to the other vertices. In either case, you should get about the same result. Okay. So this and many other schemes will get full credit if they are correct. Okay. And then there was one assumption which was expressed during the exam, which is that assume that there is no vertical or horizontal edge. That was partly for part 2, where you have to find the equation of the line. Okay. It may or may not have mattered. Okay. Assuming that makes life a little easier, but it's not necessary in this particular case. So that was the midterm review, and as I said, we'll not test exact syntax. If the main idea is correct, you will get most of the credit or all the credit. If there is a systematic problem like long int versus long int, we'll of course take care of that. One other comment, people asked where you can practice solving problems like this, and if you look at the main course page, then on the right side panel there is a link to all earlier offerings, and in many cases old exams are linked through. So there is enough problems to practice on if you are looking for them. So we get back to arrays and loops, and last time I discussed merging two sorted arrays, but since a lot of the class was not present, let me go through it again somewhat faster because we have the animation to help us. So suppose I have two arrays, and by the way, some people are still not comfortable with how arrays are declared or accessed. So the syntax looks deceptively sort of confusing. Both the declaration and access uses the box bracket notation. You declare by defining the type of the array. followed by the name of the array, and then inside box bracket the capacity of the array. Whereas you access using the same name and some index, where the index has to be between 0 and capacity minus 1. Okay. So coming back, suppose you are given two arrays which are, say, double precision, A with m elements, B with n elements. Elements may repeat, but these two arrays are individually sorted. The output is an array whose size is the sum of the input arrays, m plus n. And the goal is that C will contain all the elements of A and B, including repetitions. And C has to be also sorted. C should be in increasing order, just like A and B are in order. So that's a merge of the two arrays. For example, if A is 0, 2, 7, 8 and B is 2, 3, 5, 8, 9, then C has to be their merger. If that results in duplicate, so be it, it has to be sorted. So 0, 2, 2, 3, 5, 7, 8, 8, 9. That should be the sorted array. Now the merge approach is fairly simple. We have all done that, like card shuffling and so on. Or even in the TAs will have to take all your answer scripts and check the roll numbers and merge them from arbitrarily collected piles. So it's the same as that. You maintain two indices, AX on A and BX on B, which are also called cursors. And at any point, AX points to one place, BX points to one place, look at those two values, pick the smaller one, send it to the output, okay? And then whatever value you have consumed, you have to advance the cursor for that. So if comparing 0 and 2, I send out 0, I consume that 0 from the input A, and therefore AX has to switch to the next position. Now I compare 2 and 2, and let's say arbitrarily again the upper one wins. Then 2 is sent out and AX again advances to 7. Now I compare 2 and 7, and this time BX's contents win. So 2 is passed out and B advances to the next place. So this keeps on going. In every step you compare the head of the two queues, so to speak, and then take the smaller guy and advance that. So 3 is copied out, BX advances to 5, BX wins again, advances to 8, now AX wins, advances to 8, and so on. Okay. Now this ends in a couple of ways. Suppose the two arrays are exactly the same length and they have strictly interleaving values, you might have them end up at about the same time, but in any case what happens is one array gets over first, okay, and then the other array is left with something. And no matter what that remainder is, it's always larger numbers than anything you have passed out to the output so far. So now you have to just clean up the remaining non-empty stream to the output. So the code looks like this. A and B are suitably initialized by some other code, which we won't show. Initialize the three cursors. A and B are, AX and BX are what are called read cursors, because we'll use them to read A and B, not write them. Whereas CX is called a write cursor because we'll use it to poke values into C and advance CX. Okay. Now we put up this loop, which is best written as a while loop in this case. Okay. While AX is less than M and BX is less than N, which means while there are elements left to consider in A and B, both. Okay. We look at the head elements, A of AX and B of BX. We compare them. If A wins, namely it is smaller, then we set C of CX to be equal to A of AX, and we advance both the write cursor and the read cursor which we used, which is AX. So we write C of CX plus plus is A of AX plus plus. Otherwise B wins, okay, even if they're equal, say B wins, then we set C of CX equal to B of BX and advance those two cursors. At the end of this loop, because of the loop condition here, at least one of the arrays will be finished, over, okay. So we just put up two loops saying while there are remaining elements in AX, just append those to C. While there are remaining elements in BX, append those to B. In reality, exactly one of these loops may execute or none may execute. Okay. So that's the merge code. Now this suggests another way to do sorting. Suppose someone gave you an array whose length was a power of 2, just for convenience. So suppose I was given an unsorted array of length 8 elements. Instead of looking at that array as 8 unsorted elements, I could conceptually break it up into 8 arrays, each with one element. Right? Now an array with one element is by definition sorted. So we start with 8 arrays having a length of 1, we call them segments of length 1, which are already sorted. And then we take 2 of them at a time, and then we merge them. This gives us merged sorted array segments of length 2 each. So you end up with 4 segments of 2 elements each, which are individually sorted. Then we merge pairs of those. So we merge 2 element arrays with 2 element arrays to form 4 element sorted arrays. Okay, so we get 2 of those in position 0 through 3 and positions 4 through 7. And then we do one final merge to have one big sorted array. So this is called merge sort for obvious reasons, and the picture explains it perhaps a little better. So initially we start off with one array which we mentally break up into 8 pieces. Okay, so they are slightly gapped out, and each yellow block is a 1 element sorted array. Now we take 2 and 2 of those, and then we merge them into those segments. Okay. So now we have joined them together to represent the fact that each block is in increasing order within itself, but across blocks it could be arbitrary. So we do that, and then in the next step we put 2 of those together, and we get 4 element arrays which are in sorted order. And finally we have a single block of 8 elements which we will ensure is sorted, because we already know how to do merges of sorted runs. Now recall that earlier we said that RAM can be read at approximately the same speed no matter which location you are reading, but hard disk takes a lot longer to access because the head has to be moved to a particular cylinder or track, and then the disk has to turn to transfer the bytes in or out. The nice part about merge sort is when your runs get long enough near the bottom of the run, then your blocks that you access from memory or disk become very large. You access them strictly sequentially. Remember the code here, right? So the code strictly advances AX and BX and CX. You never go back, you don't jump around at random like pause. It's a very regulated access, just forward in the 3 arrays. So this is very friendly to disk access, because the head needs to be positioned only once, and then you just scan forward from the head position in each case. Okay, so it's all very sequentially accessed, and it's very efficient to run on hard disk. So merge sort is the sorting method of choice if you are sorting arrays which are too big to store in RAM and they're actually stored on hard disk. We will see examples of that when we do I/O, input output, later in the course. So let's analyze the time taken by merge sort. In one merge, if I am merging together AM with BN, clearly the time taken is about proportional to M plus N. For every item of output I send to C, I am doing a constant amount of work. I am comparing 2 numbers, I am copying one of them out, and I am stepping forward 2 cursors. It's a constant amount of work. So the time taken to merge AM and BN is some constant times M plus N, some small constant times M plus N. Okay? And you can test this easily by timing the merge code that I will put out on the website. Now suppose the array to be sorted is S, which has size 2 to the power P. We started out saying in merge sort, let's assume that the input size is a power of 2. Now in the first step, we imagine that these are actually 2 to the power P 1 element arrays. We pair them up and we merge them, right? So the number of merges is actually 2 to the power P minus 1, and the total time taken in each merge is about 2. So the total time is again 2 to the power P. Okay. So if you look at this picture, in the very first step, merging these two takes 2 units of time, that takes 2 units of time, and the total number of merges is 4. So I still take total of 8 time for the first step, going down from here to there. In the second step, to merge these 2 arrays, I take time proportional to 4, okay, but there are only 2 of those. So I again take time 8, okay. So every step the time doesn't change, it's just producted differently. In the second step, 2 to the power P minus 2 merges of segments of size 2, 2. That takes time 2 to the power P again. Okay. Now how many phases of merges will be there? Log of 2 to the power P, which is P phases. Okay. So in summary, we have P merge phases, each phase taking 2 to the power P time. So the total time taken is therefore P times 2 to the power P. Okay. Now, if we write n as 2 to the power p, which is the size of the input array to be sorted in the first place, then p times 2 to the power p can be written as n times log n, which is optimal because we already argued that any sorting algorithm which is based on comparing two things cannot really sort all possible n factorial inputs with less than n log n comparisons. So, to within a constant factor, this algorithm is optimal. Okay. So, we have seen now two sorting algorithms. One is selection sort, which picks the smallest element and pulls it up to the left. That takes order n squared time, which is not optimal. And we have seen merge sort, which is n log n time and is optimal. Not only that, merge sort is very friendly to disk access. It makes sequential accesses over 3 arrays at a time, okay, or 3 array segments at a time. Now, the index arithmetic involved and bookkeeping in doing merge sort is a little complicated. It's not too bad, but we'll look at it at the end of today's lecture if we have time. Okay. Comparing two elements takes a constant time. If you're comparing two integers, that takes constant time. If you're comparing two doubles, that takes constant time. But if you're comparing two strings, remember the code for comparing strings. It has to run through every character. Okay. So, primitive objects of constant size, those can be compared in constant time. But if you're comparing two strings, that will take time roughly proportional to the length of the string, or at least where the first disagreeing character appears. You have to run through that. So, we'll come back to index arithmetic for merge sort in a bit. Any questions about how merge sort works? So, the base case is an array of one element which is by default sorted, and then you keep merging upward from that. This basic technique of doubling or squaring is very fundamental to computer science all over the place. So, we saw about fast exponentiation using the squaring method. Now, we have seen this doubling method where every step the sorted runs double in size until they reach the whole length of the input array. Okay. Now, suppose I have a sorted array, how do I search it? Okay. Given an array like 4, 9, 13, 16, 17, 22, suppose the query is find the position of this number called q or query, which is 16. And in this case, the answer is 3. Okay. 16 appears at position 3, 0, 1, 2, 3. Now, maybe by convention, when you do a search like this, you declare that if q is not found in the array, your reply should be say -1 to designate that it was not found anywhere in the array. Return some illegal value, which cannot be a legal index into the array. Why do we care about searching? Suppose we have an income tax department database where there are multiple arrays, each array holding one aspect of your income tax record. The first array could be the PAN, okay, the personal account number, and there are as many elements in this array as the number of people, at least with PAN numbers. And this is sorted so that we can access people fast by PAN number. There is a second array which is income, again as long as the number of people. This is said to be ganged to the first array if every index is for one person. Of course, the second array will not be sorted unless PAN numbers are issued in increasing income order, which is unlikely. Okay. So, to find out the income of a person, you read their PAN number, you access the index at which that person occupies the PAN number and the income in both arrays. So, to draw a picture of ganged arrays, here is the PAN array, here is the income array. And one person occupies the corresponding index of both arrays. So, the PAN number is here and the income is there. If I have to access this by PAN number, it makes sense to sort this in increasing order so that I can search it efficiently. Okay. So, I find the index of a specific PAN and then I access the person's income at the same index. How do I do that? Linear search, which is what you would have to do if the array was not sorted, just check through all the elements of the array until it finds the element a of ax equal to q. That's the test condition here. A of ax is equal to q. And in this case, it outputs the index ax and breaks. If throughout the for loop this condition was never met, then by definition at the end you will end up having ax is equal to an. Okay. This is a useful test of normal termination of a loop. So see what's happening inside the for loop. All I'm doing is checking if the element matches the query. If that was never satisfied, then you end up the loop with Ax equal to An. This is a standard test to see if the break was ever taken or not. If the break was taken, you will have Ax strictly less than An. If the break was never taken, you will have Ax equal to An. Then you can output -1 or that the record was not found or something like that. Okay. Now, of course, many of you will realize that it is inefficient to search through the array if the array is already sorted, and we can instead do binary search. Okay. The basic idea in binary search is that we will maintain a bracket, a range of indices which may still possibly contain my query Q. And outside that bracket, I am convinced that Q could never appear. Okay. I will do that by initializing two indices, low and high, initially to 0 and to n-1. And then I'll keep bisecting it. Okay. I'll keep bisecting the segment with mid equal to low plus high divided by 2. And then I will compare the query with the middle element. Okay. If the query is equal to the middle element, then I've already found what I wanted. If the query was less than the middle element, then surely my answer, if at all there, has to be in the first half of the array. If the query was greater than the middle element, then my answer, if there, has to be in the second half of the array. So I can change high and low suitably. In the first case, I should change my high from the original value of high to mid -1. In the second case, I should change low to mid +1. Okay. So here's the picture. I start with Q equal to 16, and the box shows the indices at the bottom and the values inside the boxes. Now I start with low and high set to 0 and 5. So the value of low is 0, the value of high is 5. Low points to the array element value 4, high points to the array element value 22. Okay. So in the first step, because low was 0 and high was 5, mid will be equal to 0 plus 5 divided by 2, which is 2 in integer arithmetic. So mid points there at 13. At this point, if I compare A mid with Q, I will find that Q is larger than 13, and therefore I can eliminate the lower half of the array approximately, and low now points to 2 plus 1 actually. Okay. And then I'll find the mid position to be equal to 3, and then 16 will match that, and then I'll exit the loop. Okay. Now, do we terminate when low is equal to high or otherwise? So index arithmetic takes a little bit of care. In any case, before the first halving of the array, the bracket has all the n candidates in the array. After the first halving, it approximately reduces to n over 2. After the second halving, it reduces to n over 4. So again, we have this doubling trick, and the number of halvings required to either locate your query or to make sure that the query element is not there will be at most about log n. Okay. So if the array is sorted, you can search it in log n time. If the array is not sorted, then in the worst case, you have to run through the whole array. That's why we want to keep arrays sorted. That's the rationale of sorting things. You can search for things much faster. Now to implement, we need a little care with index arithmetic, because as we've already seen, if low is equal to 2 and high is equal to 3, then low plus high divided by 2 is again low. So to make sure you don't miss some elements or fall into infinite loops, you have to code a little bit carefully at the edges of your iteration. So this will work in all cases. Low equal to 0, high equal to n-1, initialize answer 2 equal to -1. Answer is the index at which the element has to be found. Int mid, and while low is less than equal to high. Okay. Int mid is their average with a round off discarded. If Q is less than A mid, then high is mid -1. If Q is greater than A mid, low is mid +1. If it's equal, then answer is equal to mid and break. Okay. Now, what do you do if answer is -1 at the end of the loop? You could either report -1 saying the array element query was not found. It's also conventional to return the negative form of the index where the query should have been inserted. Okay. So you'll sometimes see C and C++ or Java libraries not returning a -1, but returning minus of a number which when negated would give you the right place to insert the new element. And that's often useful if you now want to insert a new pan number into the array. Okay. So that's binary search. Any questions on this? On binary search? So the summary is I don't want to search the whole expanse because I know it's sorted. I'd rather use a bracketing technique. I'll initially have the bracket cover the whole array. In every step I'll find the midpoint. I'll see if my query should go to the right or left half. Accordingly I should shrink either the left or right part of the bracket. So let's spend some time coding this up to see how it works. So as you have seen, you can also declare a static array which is not changed. So you can say int a, not give a size because the size will be clear. Let's give that sorted array that we had in the example. Okay, that's also acceptable. The length is implicit. We know what the length is. But just for do something about it. So let's say an is equal to 1, 2, 3, 4, 5, 6 elements, right? Now there is a way to avoid this magic. So I have to count by hand and say 6. If tomorrow a different programmer adds an element here and forgets to update the 6, there could be a problem. Okay. So we'll see how that can be bypassed a little later. And suppose I say int query is equal to say 16. Okay. Now I'll paste in that other code. But I'll print a few things on the way so you can see what's going on. So I initialize it to an minus 1. So at every stage, I'll first print out low and high. Fine. And then maybe I should also print out mid. So let's compute mid and then print out mid as well. And then I do the comparison, and if I find it, I break. And then finally I'll print out ans. So the code is the same, just doing a few printouts. Query is 60. So low is 0, high is 5. Remember the an was 6, so I initialized to 5. Mid was 2. Okay. So some comparison happened. Next bracket became mid plus 1, 3 to 5. Okay. And in the next, it was 3 and 5, so mid was 4. Okay. Mid 4 meaning 4 is here, 0, 1, 2, 3, 4. That was too high. So now high became 4 minus 1, 3. So low and high were both 3. Mid became 3. The comparison worked out and I exited the loop. Okay. Now if I ask for something that's not there, like 15, I end up with minus 1. But the last place I checked was 3. Okay. It was bracketed between 3 and 3. There was nowhere else to go. Q was not equal to A of 3. So I exited with minus 1. But observe that 0, 1, 2, 3, 3 is here, and if 15 had to be inserted, it had to be inserted at 3. So you can instead report something like that. Okay. Would you report minus 3? That's not such a good design to report minus 3. Why is that? Because 0 would be an ambiguous situation, right? If you didn't find the element, right, but it was supposed to be inserted in the beginning, like suppose I said 2. 2 is not there. I run this and I get -1, but look, mid was 0. So it's not a good idea to report minus mid in that case. So in fact, what Java does is to return minus mid minus 1. So in case of a legal match, you'll always get 0 or positive values. In case of an illegal match, you'll always get negative values. Okay, but you can, from that negative value, you can easily derive the correct point of insertion. Okay. So you understand the reason for this policy, right? You shouldn't report minus mid because it might be 0 and then you won't know. So it's good to have a convention that not found is strictly negative, found is 0 or positive, but the negative value can be encoded to return the position where you have to insert, in case you have to insert a new person's PAN number. Okay. One more comment about the Mergesort. Suppose my specification was not to retain duplicates, but to squeeze out duplicates. You realize that as I am scanning those two cursors and sending output, I can always remember the previous value, and if the next incoming value seems to be a duplicate, I can always throw it away. So Mergesort is also an excellent way to do what's called merge purge, which is to remove duplicates from the incoming stream. Okay. So that is binary search for you. The code will of course go on the site. Okay. The next problem we'll look at is very related, which is median. Now suppose I am given a sorted array A with n elements. By definition, depending on whether n is even or odd, the median is either at A of n over 2 or it's at A over n over 2 and A of n over 2 plus 1. If the array is of even size, there are 2 medians. If the array is of odd size, there is only 1 median. Okay. So finding a median is trivial if you can sort the array. Similarly, you can find quantiles, percentiles, no big deal. You sort the array. Suppose the array had 100 elements. The 10th element, the 20th element, this would be the deciles of the array. What if the array is not sorted? The trivial approach is to behave like a mathematician, reduce it to a known problem by first sorting it. Okay. This will take n squared or n log n time. So for a long time, in the early days of computer science, there was this open question whether I can find the median of an unsorted array without sorting it. It's a very, very intriguing problem. After sorting it is obvious, it will take you at least n log n time. Now it's not too difficult to see that finding a median element will take you at least n time because you have to inspect every element. Right. If I didn't inspect the last element, I can always sneakily change the last element so that it becomes your median. So there's no avoiding reading every input. So n time is required. The big question was whether you can find median of an unsorted array in n time, or do you need n log n time to sort it, or is it something in between? So it turns out that a constant times n steps are enough to find a median. The constant is a little large, maybe 11n or something like that. And the algorithm is not at all trivial. It's quite complicated. And the analysis is also fairly complicated to start with. But so I won't discuss it in class, but I just wanted to tickle your curiosity saying, okay, I don't really need to sort an array to find the median. How is that possible? Or any quantile, in fact. I can find it without sorting in linear time. But the algorithm is quite non-trivial. So we don't discuss that. I'll discuss a simpler problem, which is suppose we are given 2 sorted arrays, again am and bn. Suppose their merge is C of m plus n, and we have seen how to merge it. Okay. The goal is to find the median of C without allocating or calculating C at all. Can we do that? And we want to do it in far less time than m plus n. If I had m plus n time, I could merge it and then find the median trivially. Suppose I won't allow that time, and I won't even allow allocating or calculating C. Can we find the median of the merger of A and B faster than merging it? Okay. Now suppose here is the array A with m elements, and that's the median position of A. Similarly, here is B with n elements, and that's the median position of B. Suppose we look at those two medians and compare them. Suppose the median of A was 20 and the median of B was 27. Because 27 is larger than 20, what do we know about the setup? We know that all these elements here is larger than all the elements there. That's the definition of the median of B. But we also know through transitivity that these large elements are bigger than 20, which is bigger than those smaller half of A. Therefore, by this one comparison, I have ruled out any of these large elements as being a possible median, because there are already m plus 2 over plus n over 2 smaller elements than those. Okay. By a similar logic, you can rule out the smaller half of A as well. Okay. So I pick two elements, I compare once, and I've immediately ruled out half and half of the two arrays. So again, how long do I have to do this? Something like log of m plus n-ish time, right? So therefore, no large item can be a median. I can throw them out. And this eliminates about m plus n over 2 elements in one shot. Therefore, in log of m plus n time, I'll again find the median. I'll not have disturbed the arrays or tried to merge it at all. Okay. Any questions about this? So I'll not code this up. It's pretty easy to code it up. So we'll have it in a lab, practice lab. Okay, so let's get back to this merge sort problem and the index arithmetic that's required in there. Okay. I need some board work. I'll do it pretty much on the board. So remember, we started out with one array with 8 elements, and we imagined those are actually 8 arrays with 1 elements each. To implement that illusion, we have to do some index arithmetic. Okay. So assume that the array size was a power of 2. To keep things concrete, we'll pick power equal to 3. So 8 elements to start with. Okay. Now there will be 3 merge rounds, as we have seen in that picture. We'll mark the rounds as Px. Px will be 0, 1, 2. Okay. So power minus 1. Now in the Pxth round or merge phase, what happens? So remember, initially Px is equal to 0. In the 0th phase, there are 2 to the power minus Px sorted runs. In the 0th phase, there will be 8 sorted runs. So in the specific current iteration, this will be 2 to the power 3 minus 0, or 8 sorted runs. Each with 2 to the power Px elements. So in the first iteration, that will be just 2 to the power 0 or 1 element each. Fine. Now, how do we count them off as indices? So these things will be called runs. Okay. Initially, in the first step, each run has 1 element. In the second step, each run has 2 elements. In the third step, each run has 4 elements. In the last, finally, one run has 8 elements. Okay. So how do we index those? Runs will be indexed by Rx, is a run index. Okay. Now, in the Pxth merge phase, the number of runs is this, right? So Rx in this phase will take values between 0 and 2 to the power minus Px minus 1. Rx will take values in that range. In particular, when Px is equal to 0, Rx will take values between 0 to 7. There are 8 runs labeled run 0 through run 7. Rx will take values from 0 through 7. Now, in the original array, the Rxth run will start at original array index Rx into 2 to the power Px. Okay. So, let me write that down. So, each run, the Rxth run starts at Rx into 2 to the power Px, ends at Rx plus 1 times 2 to the power Px. What do I mean by that? Let us plug in the values for the very first one. Suppose Rx is equal to 0, Px equal to 0. Then run 0 in phase 0 starts at 0, 0 times 2 to the power 0. Run 0 in phase 0 ends at 1 times 2 to the power 0. Okay. Actually, I should write it there. 0 times 2 to the power 0 through 1 times 2 to the power 0. Okay. So, what do I mean by ends at 1? What I mean is including 0 and excluding 1. In C and C++ and Java, it is very convenient to index from a first element of 0 to a last element which is n minus 1. So, when I say this run ends at position 1, I exclude 1 and it is up to the previous one. Okay. How about the second run, which is run number 1? Run number 1 starts at 1 times 2 to the power 0, ends at 2 times 2 to the power 0. So, the second run goes from 1 to excluding 2. The third run goes from 2 to excluding 3. So, every run has exactly one element and it is indexed like this. Fine. So, how many people are comfortable with the indexing so far? Original 8 elements logically broken up into 8 runs, each run having one element. Okay. Can I have a show of hands? How many people are okay with the indexing so far in the first phase when Px is equal to 1, 0. Px is 0, pow is 3, okay. The number of runs is 8, the runs themselves are numbered 0 through 7 and the Rxth run goes from this to that. Okay. Now, let us wipe out the yellow stuff and then let us look at what happens when we go to the second phase. So, let us say Px is equal to 1. When Ps is equal to 1, we actually have one run like this, we have another run like that. Okay. So, we have 4 runs. Why 4 runs? Because we are now in this stage, Px is equal to 1, pow minus Px is 2 and we have 4 runs, each with 2 to the power 1, which is 2 elements, each with 2 elements. Now, runs are now counted between 0 to 3. There are now 4 runs. Now, the run count has decreased in the range 0 to 3. And now, where do the runs begin and end? So, in Px equal to 1, if Rx is equal to 0, so this is Rx, I have 0 times 2 to the power 1 through 1 times 2 to the power 1. That is the first run. The first run goes from 0 to excluding 2. So, the first run is now 0 and 1, 2 is excluded. The second run, when Rx is equal to 1, is 1 times 2 to the power 1 to 2 times 2 to the power 1. So, that goes from 2 to excluding 4. So, 2 and 3 is the next run. So, now by a leap of faith, you see that because Px is increasing, the number of runs is reducing exponentially, each run size is increasing exponentially, and overall the index arithmetic will work out. Okay. Now, what is the action? What does the loop structure look like? Okay. So, now with this design, we will say at the outermost loop, we will say for Px equal to 0 through pow minus 1. That's the upper loop. That's the very outer loop which controls the merge phase. Now we will say that we need to merge a couple of runs, right? So which runs do we need to merge? We will say for Rx equal to 0 through 2 to the power pow minus px minus 1, right? But this will count Rx's through each step. We don't want that. We want to take 2 at a time. We want to take 2 runs at a time, right? So let me get back to the initial stage where I have 8 runs. I want to take runs 0 and 1 and merge them. I want to take runs 2 and 3 and merge them. Okay. So instead I'll write that, so let's say for Rx equal to 0, Rx less than 2 to the power pow minus px minus 1, and the stepper for Rx will jump in 2's. So I'll say Rx plus equal to 2 instead of plus plus. So what will happen is in the very first stage Rx will point here, in the next iteration Rx will point there, and inside the pseudocode will be merge runs numbered Rx and numbered Rx plus 1. Okay. It's logically the same as saying find the sum of every adjacent element pairs in a matrix. It's like that. So suppose I told you to calculate an output matrix which has half the elements of an input array, okay, where each element in the output was the sum of 2 things in the input, 2 adjacent things in the input. Then you would again step 2 at a time and add up ai with ai plus 1, and then you say I plus equal to 2. It's the same thing here. The run is going up in steps of 2, and I'm looking at runs numbered Rx and Rx plus 1. So this is the outer loop, and then here I have to write the merge code. Fine. So let's start coding this up. We'll see if we can finish and see what happens. So I'll copy that over. I can't have 3 elements, 6 elements, so I'll actually have say 29. We still have some time left, guys. 35. Say. We can't have it sorted, otherwise what's the point? So we'll have 35 and we'll have 4. Okay, I'll just shuffle some items around randomly. So it's not sorted anymore. And I have n elements. Okay. So now I'll say for int px equal to 0, px less than, what was px going up to? 2 to the power to power, right? So power was 3. Okay. Power was 3. Okay. Now I say px less than 3 or pow plus plus px. That's the merge phase. Okay. Merge phase number. Okay. Now I say for int Rx equal to 0, Rx less than, what I want is 2 to the power pow minus p, right? Px. So what is 2 to the power? 1 less than pow minus px minus 1. Okay, I wanted to write for Rx equal to 0 to 2 to the power pow minus px minus 1, minus 2 actually inclusive. So I write that as this in steps of 2, Rx plus equal to 2. Okay, and here the code is merge runs Rx and Rx plus 1. Okay. Instead of actually trying the sort, let me print out what's happening. Okay, so I'll print out Rx here, Px here. So I'll say merge phase Px Okay, and here I'll say cout merge runs Rx and Rx plus 1. Now let's see what they translate to in terms of indices in the array. We already said that the indices look like this. So say const int L run, the left run, okay, L run begin and L run end. Similarly, we'll have const int right run begin and right run end. Okay. Now, what is L run begin? We already saw that left run begin is Rx times 2 to the power Px. Okay. So, this is Rx times 2 to the power Px is the same as 1 shifted left Px, and this is equal to Rx plus 1 times 2 to the power Px, whereas the right guys, remember that's just Rx plus 1, the next run, right, into, that's the same as L run end, because one is excluded, the other is included, okay, and R run end is just Rx plus 2 times 2 to the power Px. Okay. Now I'll print out cout merge elements starting at L run begin, okay, comma L run end excluded, okay, with elements, merge elements with elements again R run begin to R run end. So, see what I am doing? I am basically printing out the element ranges to be merged. So, I merge L run begin to L run end with elements R run begin to R run end. I am just printing out the indices, I am not doing anything on the array itself. Okay, I had 8 positions, power was 3, phases go from 0 to 2 inclusive. Inside each phase I mark the runs and then I try to print it out. Let's see if it compiles and runs, or is there a bug. So I won't do anything to the array at all. So it's a merge phase 0, merge runs 0 and 1, 2 and 3, 4 and 5, 6 and 7. Those are the 4 pairs of runs. So merge element 0, 1 with 1, 2. 1 is excluded, so it's just 0 with 1. Runs 2 and 3 is 2, 3 with 3, 4. 4, 5 with 5, 6, 6, 7 with 7, 8. In the merge phase 1, hang on guys, if I strain my voice, everyone will just suffer. So in phase 1, I have how many runs? Runs 0 and 1, 2 and 3. Runs 0 goes from element 0 and 1 to 2 and 3. Merging runs 2 and 3 means merging elements 4, 6 with 6, 8, okay, which means actually 4, 5 with 6, 7. And in the final merge phase 2, there are only 2 runs to merge, 0 and 1. Run 0 goes from element 0 through 4, run 1 goes from elements 4 through 8. Okay. So you see how the doubling takes place. There are 4 runs being merged here, 4 plus 4. There are 2 runs of 2 elements being merged here. There is 1 run or 2 runs of length 4 being merged here to result in the sorted sequence. So now let's actually run the sort and see. So we'll not just say we are doing it, we'll actually want to do it. And how are we doing this? We have to allocate a second array, say, which is the sorted array. Okay. So same size. Now that is uninitialized to garbage, we don't care. How does the merge work? We initialize int the two runs, right? So we have AX equal to L run begin, okay, BX equal to R run begin, CX equal to L run begin again. See, when we merge this and that, say we have these two runs with two elements each. In the C array, we want these four to come to the same place. So CX will initialize there, AX will initialize here, BX will initialize there. So CX will go to the same as L run begin. So this is again L run begin. We set up the beginning of the merge sort. Now we say while AX less than, what is the run size? The run size is 2 to the power px, right? Now while AX less than L run, well, we have L run end already, so we'll say while end and BX less than R run end. Okay. So that's how the merge is going on. What do? We say if, see, there are not actually two arrays, there is just one array, really. And that array is called A. Okay. So we say if A of AX is less than A of BX, okay, I do C of CX plus plus is equal to A of AX plus plus. Okay. Else if A of AX is greater than B of, sorry, A of BX, then C of CX plus plus is equal to B of, A of BX plus plus. Actually, this is fine. Sorry. Else we do that. Okay. No tie breaking can be arbitrary. The smaller or less than equal to element goes to the output. And finally, we have to clean it out. So while AX less than L run end, we have that, while BX less than R run end, we have this. Okay, you need to focus on the indices a fair bit to make sure there are no mistakes. But if you code like this, you will not usually make a bad mistake. So this is how we do the merge. So let's see if there's a bug or is this okay. Right, now at the end of each stage, let me initialize C to some actual value so that we know that it's garbage, a specific garbage value. So I'll say for int Cx equal to 0, Cx less than an plus plus Cx. Because there was no minus 1 in the input, I'll just say C of Cx equal to minus 1, say. Okay. And at the end of every stage, I'll print out C. Okay, this is the merge phase loop. End of merge phase loop. This is the end of the run loop. So between that, I'm going to print out the C array to see where C is going. So instead of writing C, I'll of course print out C of Cx with a comma. And then finally, I'll print out a line. Okay. So let me go through the circus in slow motion again. Okay. First, I put up the merge phase loop. Then inside, I put in the run loop. That's already explained on the board. Then all I did is inside the two inner loops, I put in the merge code. The merge code puts up two cursors. It just outputs the smaller one to the output. Okay. Now, of course, given the condition under which I have done this coding, there is very high chance of there being a bug, but let's check it out. Okay. I gave it an unsorted array. Let's see what happens. So clearly nothing is, this is not really working. Mod space 0, well 935, 16, 22, 13, 17, 429, that was correctly done. Okay, look, the original array was 35, 9, 22, 16, 17, 13, 29, 4. So all the 2 element sections were unsorted, right? But at the end of the first phase, at least it did the right thing. Okay, 9, 35 was correct, 16, 22, 13, 17, 429 was correct. And then it made some mistakes. Merge elements 0, 2 with elements 2, 4. That was supposed to give me 9, 16, 22, 35. So somehow that didn't happen. Okay. So the mistake was clearly in the second step. How did that happen? Okay. So I can post this code and you can investigate it to see where the bug is. Okay. Bug fixing is an important part of coding. So try it out. Okay. So I'll stop there because the sound is getting impatient.